Hello, everyone. Thank you very much, Ustad Salem, for organizing a seminar and also for Physique platform. Thank you, Professor Ahmed Ennaoui, founder of Virtual Learning University, for this initiative to create this series of lecture for young researcher and PhD student.
Thank you.
This series started last week with the first talk has been given by Mrs. Umayma bin Abdelhadi. Today we will have the second lecture, which will be given by Dr. Majid Kassaoui. Before I introduce him, I give the floor to Professor Ahmed Ennaoui to give an introduction and maybe some welcome few words. You have the floor, Professor Ahmed Ennaoui.
Thank you very much. I will share my screen. Hope it's working. Let's see. So do you see my screen actually?
Yeah.
Okay, very good, very good. So first of all, welcome all for this seminar, which are given by students, PhD student, maybe we'll also have master students in the future. So before I give the floor to the speaker, I would like to just to give some highlight. As you see here on my screen, I just draw the solar spectrum again in order to remember that we are working on sustainable development on solar energy, etc. So you have the spectra, the whole spectra of the sunlight. Then I put here a solar cell, wafer, silicon wafer. And as you see, that is the status actually of the solar cells, which are back surface field based. Then I put here electrolyzer. And as you know, the hydrogen production, green hydrogen production is we use an electrolyzer. I put also here a photoelectrochemical solar cell, which is a semiconductor, and when you illuminate it, you can produce also hydrogen and oxygen, and we will have the opportunity to give more details. What is important today is that all these items here are necessary to produce hydrogen and oxygen by electrolysis. And we talked last time about electrolysis of water, splitting of water. And I told you that you have two chemical reactions, one in the cathode and one in the anode. And between these two cathode and anode, you have a potential of 1.23 volts, which corresponds to the free energy delta G, which is related to the number of electrons exchanged. And as you see here, there are 4 electrons exchanged. And when you exchange a lot of electrons, you need to facilitate the reaction, and we need what we call catalyst or catalyst. That's one thing, what we discussed last time in a little bit of more details. And today we will go to, we suppose that we produce hydrogen, and we need to store this hydrogen. We need also to transport the hydrogen from one country to the other, or from one place to another. And we use other technology or other innovative idea to produce electricity, like, for example, for fuel cell. And there are also other end use, like mobility or a hydrogen car. In the chemical industry, the Haber-Bosch process, the methanation, these two processes are very important in the energy transition, because you can produce fertilizers with Haber-Bosch process. You can produce methane with the methanation, and you can even fix CO2 or carbon dioxide. By the way, you can also let the CO2 reacting in an electrochemical reaction with electrolyzer, and that schematic here show you different reactions which are very close to each other, which make the problem very complex. So, sorry. We will talk about the storage of the hydrogen. And one of the important method for storing hydrogen is using metal hydride. That's what will be the topic today. And you can see here that it's very important to design the solid carrier metal hydride, for example, or some porous materials for delivering hydrogen at low cost. That's one of the objectives. And then I put here different problem which has to be resolved. For example, you should have material with high gravimetric. This means the amount of hydrogen absorbed per unity of mass is very important to optimize. High voltammetric density also. We have also to find material which are very functional and very effective at temperature and pressure close to the ambient conditions. It's also very important. And also you need a high number of charge-discharge cycles. It's very important. If you have a material which will be after some time collapse, it's can be a problem. And also the kinetic, you should have a fast kinetic of charge discharge. So every time when you prepare new material for storage, all these issues are very important. The safe and the low cost, at low cost. And of course, large scale hydrogen storage is very important. I put here the end use of the roadmap of European community by 2050, and they send you on our WhatsApp group. I send you this roadmap, so you can read it when you have time. And in this roadmap, I just put here the most important. Hydrogen will provide by 2050. It will provide 24% of the total energy demand. It's up to 2,000 terawatt hour of energy. So it's very important that in a roadmap you have some numbers that you know exactly how much you will have in a given time. For example, here is 2050, and they suppose that Morocco also have a roadmap. And of course, we have to know if this roadmap corresponds to this 2 degrees Celsius scenario. This means that the hydrogen what you will produce can resolve the problem of carbon dioxide in a way that you can resolve the problem of 2 degrees Celsius to achieve this goal. That's the roadmap of Europe. I think I'm sure there is also a roadmap for Morocco. And from this roadmap, one has to do research to help to achieve this goal. Okay. I just want here to go back to this problem of electrolyzer and catalyst. And I just put here the solar spectrum, that's the input solar energy. A solar cell, you know that a solar cell will deliver a maximum of voltage and current, which is this point here. Maybe I have to show with the just let me. Okay, so here you have a maximum power point here, and this point here on the spectra it's correspond to the VM voltage in the current. This 2 point here, and integrating this IV characteristic, you will get this. And normally that's the energy you will receive on your electrolyzers, and the efficiency is given by this relation. So this means the output from your module or your solar cell divided by the solar spectrum, or what your solar cell have absorbed. And here is the area. But the problem is when you, as far as hydrogen production is concerned, you cannot get all this energy. The problem that you need a catalyst. And that's why if you look to this curve here, what I plot here, the current in the vertical and the voltage in the horizontal, you see here that if you have a very bad catalyst, this curve here, what I show you, then you will lose most of the energy here what your solar cell deliver. If you put a very good catalyst, then you will get your maximum of power here, what I show you here again. Huh? So therefore, the catalyst is very important. Even if you have a solar cell with a very high performance, if you don't have a good catalyst, you will just gain a very small area here. If you have a good catalyst, then you will get the large area. That's why the catalyst is very important. And everything is dictated by the dark characteristic what you see here. So this means the exchange current. So you can also calculate the efficiency with another relationship by using this free energy, that's a theoretical one, multiply by the rate of hydrogen, what you can measure the bubble of hydrogen, for example, divide by the energy input, which we can suppose that is 1,000 watt per square meter. Okay, so that's very important to know. I go back again, like the last time, to the photochemical solar cell. The most interesting case to produce hydrogen imitating the nature is to use two semiconductors, one semiconductor N-type and a semiconductor P-type. And we can put it together. One is a anode and one is cathode, but you have also to have a good catalyst for the N-type and good catalyst for P-type in terms of energy, because your Fermi level, quasi Fermi level here is more in the close to the vacuum, and here is very far from the vacuum. So therefore, when you are looking for a catalyst, you have to take this into consideration. Okay. last but not least, I want just to show you how I see the research and development. We are working here for the group at the Faculty of Science Rabat. They are trying to investigate, to explore the Mendeleev table and to find a new solid state hydride that satisfies to the multitude of requirements for a practical hydrogen storage system. That's the objective. And there are a lot of requirements. I told you about some of them. Okay, I just put here some known catalysts like zeolite, for example, or new catalysts, what you can find by yourself if you use the quantum mechanics. And then, so whatever for the hydrogen storage or for catalyst, you have to predict new materials. By predicting new material, you gain time and you gain money instead of working with some material which are far away from the topic. You can do some calculation and you find some material and to try this experimentally. And then whatever you do during the knowledge development, you have to do some experiment to make a proof of concept. This means you select some material, you test it, and you see that you can produce, for example, hydrogen in case of you are looking for catalyst, or you can store some hydrogen in case where you are working on hydrogen storage system, and then you characterize your material accordingly. When you have your proof of concept, you have to identify how good this catalyst under harsh environment. Or for example, in terms of when you are looking for hydrogen storage, you have to find a catalyst which give good result at room temperature, for example. And this will bring you to a level, if you look to this technology readiness level here, which start from research, basic science, research and feasibility. You can be, after the proof of concept, you have to contact some industrial partner. If you are far and you know that you are far with your material, to help you with funding and also for testing, in order to go further until the technology readiness level 9. If you are in the technology readiness 9, this means you are really, you have a system which work very good and which can be scaled up, and you can, of course, talk about startup and about industry development. So I'm not going to show this one, but this is very important. The work, what is now done by students regarding the simulation and the modeling and testing in the lab and going back to the modeling, etc., is a very important step, what I call here knowledge development. And as soon as you start to test your material and you find that it gives some result, you have already your proof of concept, and then you have to start to go further. So that is the path what one has to follow. This is the path which is used by NASA. It's published since more than 10 years. So I will stop here and give the floor to the Majid, Dr. Majid Kassaoui, to give his talk. So,
Thank
we
you.
can discuss, of course, if you
Thank
like.
you very much, Professor Ahmed Ennaoui, for this nice introduction and very useful for future studies. It's my pleasure to introduce the speaker, Dr. Majid Al-Kassaoui. He is from the Laboratory of Condensed Matter and Interdisciplinary Science at Faculty of Science, Mohammed University in Rabat, Morocco. He obtained his PhD at Mohammed University under the supervision of Professor Abdelillah. His main research topic is focused on green hydrogen, its production and storage. He is particularly interested in the solid-state hydrogen storage. His approach is based on modeling and simulation using quantum mechanics and statistical physics. In particular, ab initio calculation, density functional theory, molecular dynamic, and Monte Carlo simulation. He is a member of the green hydrogen team at the LaMCScI laboratory at Faculty of Science, Mohammed University in Rabat, with Professor Abdelillah, Professor Mohammed, Professor Hamid Zahrawi, Professor Omar Mounkachi, and other professors in this laboratory. He is also a member of the Green Hydrogen Project team led by Omar Mounkachi and funded by OCP and CNRST. In this presentation, Dr. Majid Al-Kassaoui will explain in more detail the solid-state hydrogen storage, in particular in adsorbent materials like 2D materials and metal organic framework, which have a large specific surface area. He will specify what modification must be made to improve the performance of this material in terms of storage capacity, volumetric and gravimetric, and how to shift the desorption temperature close to room temperature. Dr. Majid Al-Kassaoui, you have the floor for your presentation.
Thank you, Hassan. Do you hear me? Can you hear me?
Yeah, we hear you and we see your presentation.
Hello, everyone. First of all, I would like to thank Mr. Ennaoui and Mr. Salim for this chance to present my work in this virtual learning university. I would like also to thank Professor Benyoussef for this invitation, and it's my pleasure and honor working with you. Hope to get the guidance and support from you out my future advances. My talk is about in solid-state materials is information hydrogen storage medium. As well known, the rapid development of the hydrogen technology and the ground energy need different in many countries to set domestic the hydrogen roadmap. It's obvious that the hydrogen and fuel cell can meet the rise in demand for the societal development, and they provide the possibility of the covering most energy fields. Therefore, the many countries, such as the China, the Germany, the Japan, include the hydrogen development in their national strategy and implement measures in promote the fuel cell industry. So my talk is allocated about the hydrogen storage field. The outline of my presentation is as follows. The first one, the problem statement and motivation in hydrogen storage. And after that, I will present an overview of hydrogen storage, especially for the metal organic framework and two-dimensional materials. And the second part, this hydrogen and or the result and discussion based in theoretical for the density function theory, simulation and modelization. And finally, with conclusion and future recommendation. Energy is one of the basic requirements in our daily lives, and the words energy demand is continuously increasing over the years. So the renewable energies such as the hydro, the solar, geothermal, and the wind sources, including the biofuels, are possible solution for the replacing fossil fuels and reduce the carbon dioxide. Fortunately, the share of the renewable energy sources is still small and definitely not enough to satisfy the world's global energy demands. As the new vector, this is hydrogen. Hydrogen is the field that has received a lot of interest due to its abundance, higher power density, and environmental friendliness. On the other hand, the hydrogen is the ideal clean for the mobile and stationary power sources, as well as the most promising alternative to the combustion of finite. And another one, the carbon rich and the environmental, the harmful, the fossil fuels, such as the diesel or the gasoline. The development of hydrogen energy systems evolve three stages. The first one, the production, storage, and utilization or distribution. So the method of production, storage, power, or the power conversion are the subject of much research. But the main obstacle is how to store hydrogen efficiently and safely under the appropriate condition or appropriate thermodynamics. First one, the hydrogen can be stored in different tanks. The first one, the compressed gas or cryogenic liquid, and the liquid H2, but also in materials. Can absorb in or can store in materials is to access the first one, the chemical option or the physics option. For example, the methyl hydride, the formic acid, the ammonia, the carbohydrate, the liquid organic, and another axis in the micropore or the nanopore materials. The advantage of these materials is higher the volumetry hydrogen density, but less the gravimetry hydrogen density. What is the criteria in hydrogen storage? The first one, the appropriate thermodynamic around the temperature or the pressure. The second, the good kinetic of the absorption, desorption, and the high gravimetry and the volumetry capacity, the high mechanical strength and durability, and the safety and the condition normal, the normal. On the other hand, the Department of Energy target celebrates in 2025 the gravimetry capacity the 5.5% and the 0.04 kilogram per liter, and the cost or the cost systems, the $300 per kilograms. So the first axis, the metal organic framework. I will give the brief story of the metal organic framework. One of the first documentation in metal organic framework was in the 1965 when the term formed, I mean the coordination polymers via the Solvautier mass design. After that, Professor Larry in 1999, they used the molecular building block approach to synthesize one of the first metallic organic framework to display the permanent porosity, namely MOF5. MOF5 is crystalline coordination polymers or polymer, which consists of the metal cluster connected by organic linker. On the other hand, there is another or a large series of isotubular metal organic framework have been products in which each member the same cubic topology, and the situation of the hydrogen storage via diffuse absorption. The MOF5 can achieve in gravimetry capacity up to the 4.5% at the 88 Kelvin. However, a common problem exists with the metal organic frameworks for the hydrogen storage. At the ambient temperature, the hydrogen absorption is too small because the nature of diffuse absorption. So, how to increase the absorption energy and the room temperature is a big challenge for the practical application. In LaMCScI, theoretically, there is several strategy or the enhancement improve or the enhancement hydrogen storage property in metal organic framework. The first one, this increase in the porosity, I mean the size or the volume and the surface specific. The second one, the doping of the metal nanoparticle and the alkaline metals. And the third one, the functionalized via the organic or the linker organic. And after that, interpretation or the catenation. And the last one, to create the strong absorption set. And this study among the quantum chemical method density function theory is nowadays one of the most popular method for the ground state electronic structure calculation because of the favorable the balance between accuracy and computation efficiency. Hence, in the recent years, DFT has been used to predict and develop the new strategy of the new materials and to understand the properties of the materials that can store hydrogen reversibility. That's good, but let me start by simulating our system in a different topic, 2-dimension and 3-dimension in hydrogen storage. The first one, this metal organic framework, the conventional structure in the metal organic framework has a cubic FM3M, the symmetry with parameters or the lattice parameters, the 25 or the 24 angstrom, and the quotient H, the primary unit of the ZN4O, the BDC3. This structure composed of the 425 atoms, which too expensive in time and requirement for the computation. Thus, to avoid the computational inconvenience, we consider in this work the simplified system named namely the connector. This connector, which is the side of the crystal structure of the metal organic 5. The first result we obtain the value of formation, energy of formation is the 13.85 kilojoule per mole. That explains the stability of the connector. Furthermore, using a Benyoussef molecular dynamic, we can see that the free energy is well converged in the given period for all the temperatures. They confirm the thermal stability of the structure. And for this, the study of hydrogen strike performance in this connector, there are three set adsorption. This is a metallic set, carboxylic and cyclic, with free orientation, horizontal, vertical, and sloping. As shown in this figure, among the different set of adsorption, the cyclic with the sloping orientation one appears as the most favorable for adsorption in single hydrogen molecule. Within the value Bedian or the adsorption energy is equal to minus 37.80 kilocalorie per mole. Let's talk about the strength or the mechanism of interaction between the molecule hydrogen and the surface. It's important to calculate the density of state before as well as after the adsorption of H2. After the hydrogen molecule, there is the new strong hybridization once appear between the H atom with the carbon and H with the oxygen atoms. There is another parameter. This is H2 kinetic or the migration between the adsorption set in the surface or the inside connector is playing its crucial and the kinetic instability. Therefore, we simulated in the diffusion of the hydrogen molecule H2 via the connector and to pathway between carboxylic or the metallic carboxylic and carboxylic cyclic. It's found that the barriers of migration of the hydrogen molecule in sloping orientation are higher than that of diffusion along the horizontal and the vertical orientation. To add several hydrogen molecules in the surface, as shown in this table, for horizontal and aclinic or the sloping orientation, the number of the adsorbed molecule is important up to the 12 hydrogen molecule, while for the vertical orientation, the connector can absorb only the chain molecule of the hydrogen with any deformation structure. And for assessment of hydrogenation of connector properties, the parameter or the volume connector increasing while the decrease while increasing the number of hydrogen molecules. Similarly, for the hydrogen absorbent capacity, the 4.57% in the case of horizontal and inclinic, but for the vertical orientation is equal to 4.09%. These values are lower than the optimum values proposed by US Department of Energy. To improve the hydrogen storage capacity of the metal organic framework, we have carried out the strategy of two phenomena. At the same time, the first one consists of substituting the Zn by cadmium and magnesium atoms, and the second one investigated the effect of the decoration by three elements: lithium, barium, and sodium atoms in the most absorption set. I mean the organic linker. And the values or different values of absorption or the binding energy is as follows. So, moreover, we studied the absorption energy of single hydrogen molecules on the surface functionalized by three elements on both sides, the lithium, sodium. Firstly, a reduction of the absorption energy is observed compared to system without decoration for free orientation. And secondly, the horizontal orientation for the absorption hydrogen molecule is more absorbing than vertical and sloping. In the same reason, for the computation study of the Zn functionalized in hydrogen storage, we obtained the 6 molecules of the hydrogen quasi-molecular from the cyclic set, I mean around the cyclic set. In the moreover, the beryllium on both side element can only absorb the 5 molecules as the maximum quantity of the hydrogen per organic linker. And this table here, they present different values of average absorption energy and the different distance between the HH and the element decorative with molecule H2 and gravimetric capacity and the parameters, the desorption temperature. In general, we conclude that the metal organic framework 5 based the metal magnesium with 2 elements or the element on both sides, the lithium. This is more suitable for hydrogen storage application as the metal organic framework 5 at ambient temperature. Also, the obtained the temperature is very close the desorption temperature range of magnesium hydride MgH2, which figures among the most attractive materials for the hydrogen storage. As a second axis to dimensional materials, structure show profound efficiency in molecular hydrogen storage by providing large surface structure diversity, excellent phase absorption, and thus every additional absorption set to ensure or the incorporate molecular hydrogen. And to evaluate the stability of the metal organic framework in the surface or the tetragonal graphene monolayer, this table or the according to this result of table, the obtain the values of the binding energies are the smaller than the cohesive energy or relative to the bulk metal. The metal of the lithium, sodium, potassium, and calcium, except for the case of the scandium that has the binding energy higher than the experimental cohesive energy. This result shown that the agglomeration do not occur in the case of the lithium, sodium, potassium, and calcium, but it's possible for the scondio. To be able to verify this possibility, we calculate the energy barriers for the diffusion of the scondium atoms from the most adsorption set to other ones. This value is higher, therefore the presence of the higher diffusion energy barrier can restrict the transition of the metal atoms and prevent the system from crystalline. Then we can see the bit energy increases while the increase in the number of metal atoms. The decorated elements are still dispersed and the tetragonal graphene without the crystalline. For the case hydrogenation maximum, the system reaches saturation for the 20H2 for the lithium, sodium, potassium, and calcium, and only 19H2 for the case of the scondium. The best element is a lithium with gravimetric capacity in the 8.41, but less the gravimetric or the less the desorption temperature. In the context, the novel two-dimensional materials or the borometry, tetragonal borometry, this B4N4 within structure similar to the graphene, which is the inspired used to study the hydrogen storage properties of these materials. According to what has been mentioned before, and due to its light metals, the bidding strain of the lithium atoms on tetragonal borometry is stronger than that on tetragonal graphene. Also, weakening of the electrostatic or the charge transfer from the first the lithium decrease from the 090 to the 083 electron. A weakening of the electrostatic attraction with the host materials based on the pedos on the after decoration. The peaks of the hybridized orbit between the lithium and the boron, especially for the p orbital, are mainly located above the Fermi energy and the reset, and the lithium atoms strongly bond with the tetragonal borometry. By adding additional H2 molecular, it was found that the system can absorb up to the 32 H2 before the formation of the system, with average absorption energy 0.386 and 0.217 electron volt. Also, the gravimetric capacity reaches the 12, the excellent capacity, 12.80 or 47%. The maximum desorption temperature is equal to 161.03 Kelvin. And now the thermodynamical stability by using ab initio dynamic moleculars. We first start the IMD simulation at the 100 Kelvin, shown that all the hydrogen molecules remain around this element and surface. Once the temperature rises and the maximum number of hydrogen molecules have moved far enough away from the substrate and this element. For the single H2 or the H2 kinetic, In general, the fast diffusion of hydrogen molecule into dimensional materials moving across the surface is crucial for the development of the next generation energy storage devices. We can observe in both systems that the hydrogen molecule is diffused via the bit 1A. The minimum diffusion barrier is the 9.80 millectron volt and 13.6 millectron volt. These values are the law compared with the values the value of the 14 in graphene. Moving on. There is another molecule or the system molecule is beryllium carbide. This structure crystallizes within the frame 1, the space group in the form of hexagonal structure similar to that of graphene, but with 3 atomic layers along this direction. The upper and the lower layers are the beryllium atoms, and the middle one layer is the carbon atoms. In distance between this layer, this 0.90 angstrom. According to our computation and the different or the values approximation, the beryllium carbide has an inclusive energy of the 5.78 electron volt per atoms, indicate the energetic stability, the stability of the beryllium carbide structure. And also it has very good dynamical and thermal stability by using the difference spectral and the Benyoussef molecular dynamic simulation. For hydrogenation or the hydrogen interaction, figure summarize the different values and the different set absorption in the surface. For example, the best set absorption, this is about the beryllium with the minus 228 millectron volt. Next, we will employ the novel strategy to improve the hydrogen storage properties of the system by studying the hydrogen absorption on the metal decorated the beryllium carbide. There is values of the bed energy on one side and one both side, and also it can be seen that the oscillation of the total energy of all considered the system are the stabilized over the dynamic molecular time. Moreover, in this here, better charge atomic analysis was performed to quantitate the number of the electron transfer during the decoration processes. Results shown that over the best or the most absorption set, the charge state of the lithium, sodium, calcium, and magnesium are the 0.70, 0.55, 0.57, and 0.20 electron. This means that the metal atoms become the cationic after absorption, which is the beneficial for hydrogen storage. Based on the average absorption energy, the successive energy, we conclude that both systems reach a saturation at 16H2 hydrogen molecule, with stable absorption energy and any structure deformation. At the maximum H2 coverage, the gravimetric capacity of the the 10.21% and the 8.48% for the lithium and potassium respectively. And the desorption temperatures are the much higher than the critical temperature of hydrogen. And finally, the thermodynamic of adsorption hydrogen molecule. At the one hand, we can say that the hydrogen molecule is moved noticeably far away from the metal decorated and the substrate at ambient temperature. All H2 molecules moved from the metal atoms, and some of them have been removed from the structure within small congregation along the Z direction. Thus, this result supported the event of desorption temperature estimation. In conclude, or the density function or density function theory calculation, we place an importance in designing the strategy as the theoretical calculation are the effective way to avoid the expensive trial and the error process of the experimental laboratory. The second one, the new approach aimed to tame the hydrogen storage properties of the metal organic framework 5. And the third one, our study demonstrated that lithium decorated the barium carbide or the tetragonal brominated monolayers could be considered as promising host materials with the great physical characteristic and the high gravimetric capacity for hydrogen storage. For the proposed future research, we can employ another methods to create the strong bidding set, or the materials design based on theoretical prediction by using the density function theory or the dynamic moleculars and Monte Carlo cinetic. This work has resulted in the many publications in international journals with the high impact. With I would like to thank my hydrogen groups, and Mr. Benyoussef, Mr. Kenz, Mr. Lugili, and Mr. Mohan, and Monsieur Omar Mounkachi. Thank you for your attention.
Thank you, Dr. Majid Kassaoui, for this nice presentation on two-dimensional materials and metal organic framework, which are very promising for the solid state storage of hydrogen. Before I open the floor for question and comment, I give the floor to Dr. Haji, Mohammed Haji, from the team of Green Hydrogen Project, led by Professor Omar Mounkachi, to give a brief description of the projects. Haji, you have the floor.
Maybe Ustad Salim should include him in order to.
Oui, monsieur Benyoussef.
You have it. Okay.
Oui.
Very good.
Yeah.
Je vais partager simplement l'écran.
Okay.
D'accord, il y a toujours la désactivation de partage. Je n'arrive pas à partager mon écran.
Ustad Salim, could you please allow him to share his presentation?
He can.
Okay, thank you.
Okay.
just go downstairs to the green arrow where it's written partager l'écran.
D'accord, c'est bon, ça marche. Je partage. Donc là, vous avez une visibilité sur mon écran?
No, you have to open your PowerPoint also.
First, open the PowerPoint and then share it.
Là, vous voyez mon écran?
Non, non, pas encore, Mohammed.
Open the PowerPoint first.
Oui, il est déjà ouvert.
Donc, share the screen. Downstairs there is partager l'écran. Then you open it. Then you see by yourself your screen. Twice. You have to do it twice.
Là, vous avez...
No.
Toujours rien? Parce que je viens de partager l'écran.
We don't see it, no.
Vérifiez, est-ce que votre fichier n'est pas protégé?
Or you can just show up and talk directly about the project. You don't need to.
Okay. Without support. Okay.
Just show up, open your video, and start to talk about the project. Yeah.
Okay.
Now we see it. Now we see it.
And now we see.
Là, très bien. Donc,
Very good. Very good.
très bien. Je vous remercie. Je m'excuse pour cette faille. Donc, je vous remercie, monsieur Ennaoui, monsieur Benyoussef. Donc, tout d'abord, je voulais représenter mes remerciements au nom de l'équipe hydrogène ici à Rabat pour la comité d'organisation, que ce soit pour monsieur professeur Mohammed Abdelillah Benyoussef, professeur Ennaoui et monsieur Salem Rajab pour cette opportunité d'exposition de nos travaux de recherche et d'échange entre plusieurs chercheurs dans le domaine de l'énergie à travers cette plateforme de l'université virtuelle. Donc, étant donné que mademoiselle Oumaima, qui est présentée la semaine dernière, et docteur Majid Kassaoui, qui vient de finir sa présentation, font partie de l'équipe hydrogène, qui travaille actuellement dans le cadre d'un projet recherche et développement sur la thématique du réservoir et de métallique. Donc, également à la demande du professeur Omar Mounkachi, coordinateur de ce projet. Donc, je voulais profiter de l'occasion pour donner brièvement une idée sur ce projet et ses objectifs, tout en indiquant ses axes de recherche. Donc, comme ça a été mentionné par professeur Benyoussef, je suis Haji Mohammed, donc docteur en sciences de la matière physique, spécialité énergie renouvelable et sciences des matériaux. Donc, actuellement, je suis chercheur postdoc au sein de la faculté des sciences de Rabat dans le cadre de ce projet. Donc, quand je viens de mentionner, les travaux de ce projet tournent autour d'un réservoir à hydrure métallique à grande réactivité, dans l'acronyme H2PSC, production, stockage et conversion. Donc, il y a plusieurs partenaires au niveau de ce projet, comme l'UR, l'Institut Niel, l'IRESEN, l'Université Mohammed VI de Ben Guerir, l'ENSA de Rabat et d'autres encore. Donc, la motivation, pour ne pas tarder, la motivation qui nous a poussé à travailler sur cette thématique, c'est d'abord le mouvement actuel sur l'hydrogène, que ce soit à l'échelle internationale ou locale, ainsi pour avoir un lien avec la stratégie du royaume actuel sur l'hydrogène et les énergies renouvelables. Et parmi les applications qui sont ciblées par ce projet-là, il y en a plusieurs, mais on se focalise tout d'abord sur l'aspect mobile, sur l'application mobile via la pile à combustible, Il y a également la gestion ou la production d'énergie, que ce soit de l'électricité ou de la chaleur, à partir de l'hydrogène. Et également, bien sûr, l'effet de cette production de l'hydrogène vert sur la production également de l'ammoniac vert. Donc, sinon, pour les objectifs de ce projet, il se résume en 4 points. Tout d'abord, l'étude et la mise en place d'une chaîne autonome de production, de stockage et de conversion en 2 phases. La première phase est à l'échelle laboratoire. Donc, c'est la mise en place de cette chaîne à échelle laboratoire avec une capacité minime afin bien sûr, cette installation va nous permettre d'anticiper les besoins futurs pour la mise en place à grande échelle ou à moyenne échelle avec des capacités plutôt supérieures. Donc, pour la mise en place à moyenne échelle, on va utiliser des équipements qui sont déjà disponibles chez l'un de nos partenaires avec des capacités supérieures, comme un électrolyseur de 20 kW. Également, on va essayer d'élaborer et de réaliser 2 réservoirs, un d'une capacité de 5 kg avec nos partenaires français. Et le deuxième sera, on va essayer de le faire 100% marocain avec une capacité de 2 kg et qui sera réservé bien sûr pour l'installation à laboratoire. Donc, le troisième objectif qui est indispensable à cette chaîne, c'est la réalisation et l'étude de ce réservoir de stockage solide. Et vers la fin, on va essayer de mener une étude techno-économique au niveau de 2 régions ici au Maroc, la région de Marrakech ainsi que la région de l'Aïoun, puisque ces 2 régions disposent des plateformes nécessaires pour la production d'hydrogène, à savoir bien sûr des installations pour l'énergie verte, comme par exemple la province d'Orhamna à région de Marrakech. On va utiliser les plateformes disponibles chez Green Energy Park, puisqu'ils disposent des plateformes d'énergie solaire, ainsi que l'électrolyseur et une unité de dessalement. Pour l'unité de dessalement, ça sera la dernière partie. Donc, on ne se focalisera pas au début sur l'unité de dessalement, mais ça sera par la suite, parce que si on évalue cette chaîne, on doit répondre à une certaine exigence de l'eau potable. Donc, on ne peut pas utiliser l'eau potable pour la production de l'hydrogène, surtout en ce moment même avec des problèmes de désertification, manque d'eau potable, etc. On ne peut pas justifier l'utilisation de l'eau potable pour la production de l'hydrogène. Donc, ce n'est pas une priorité. Donc, du coup, on doit envisager une production à travers le dessalement d'eau. Donc, on doit fournir de l'eau à l'électrolyse à travers le dessalement d'eau. Donc, ça, c'était en gros l'objectif principal du projet, la réalisation du réservoir, la réalisation des 2 chaînes de valeur de l'hydrogène et pour finir, l'étude techno-économique pour essayer de voir est-ce qu'il y a la possibilité pour une validation industrielle et pourquoi pas commerciale avec bien sûr nos partenaires. Donc, pour cela, les axes qui sont ciblés par ce projet-là, il y en a plusieurs et ils sont divisés en 2. Donc, il y a un axe matériaux et un axe système. Pour l'axe matériaux, il est réservé bien sûr à l'étude de stockage solide d'hydrogène. Donc, ainsi que l'étude du matériau de changement de phase pour le stockage de la chaleur de réaction, parce qu'on doit gérer la chaleur de réaction lors de l'absorption pour ne pas affecter le taux d'absorption de l'hydrogène au niveau des hydrures. Et dernièrement, le matériau électrolyte pour bien sûr la production d'hydrogène. Et pour la deuxième partie du système, elle est réservée à la conception, bien sûr, du réservoir. Ça veut dire l'enceinte porteuse des passés d'hydrure de magnésium qui doit, bien sûr, donner la possibilité de gérer la température, gérer la pression lors de l'absorption et désorption. Et ainsi que l'unité de dessalement. Et il y a également la partie réservée à la mise en place de la chaîne. La mise en place de la chaîne elle-même, elle est bien sûr décomposée en 2 parties. Partie de simulation pour voir comment le comportement de chacune de ces technologies en couplage, donc voir leur comportement en couplage, et pour finir, pour faire une mise en place tout entière puis la production jusqu'à la conversion. Donc, pour, comment dire, avoir la possibilité d'étudier ces deux axes-là, on va utiliser les différentes méthodes qu'on connaît, que ce soit la DFT, Monte Carlo. Il y a également de nouvelles modélisations sur MATLAB, sur Fluent, pour essayer de développer tous les axes qui sont nécessaires pour la réalisation en bon terme de ce projet. Donc, pour ne pas tarder, c'était simplement pour donner une idée claire sur les différents axes ainsi que les objectifs phares de ce projet. Pour finir, je voulais bien sûr, puisqu'il y a Monsieur Salem, pour donner une idée, je vais donner un petit résumé en anglais. Donc, to give a summary in English. So, by this presentation, I would like to give a short idea about the project of hydrogen conducted by our team here in Faculty of Science in Rabat at Mohammed University. As you have seen, the objective of this project is developed and realized a meter hydro tank and studied and establishment a hydrogen value chain from production to conversion based on solid state storage. So through this project, several lines of research are tackled. For example, solid hydrogen storage, led by Dr. Majid Kassaoui. We have electrode materials studied by Mrs. Omaima. And we have also studied about solid hydrogen storage tank configuration, studied by Huda Al-Alam. Where she studies the thermal comportment of the tank for a great management of heat of absorption reaction in order to maximize the performance of this tank. And finally, we have the study about the hydrogen value chain by a MATLAB to maximize the energy production by every equipment coupled in this chain value. Donc, je vous remercie encore une fois, Monsieur Benyoussef et Monsieur Ennaoui pour cette opportunité de présenter bien sûr notre projet au sein de cette université virtuelle.
Micro, monsieur, micro.
Monsieur Benyoussef, votre écran, votre micro.
Okay. Thank you very much, Dr. Majid Al-Kassaoui Mohammed Haji, for this nice presentation of this promising project of green hydrogen from the production to the storage. Now, I ask Professor Ahmed Ennaoui to comment on the Dr. Majid Al-Kassaoui talk. You have the floor.
Yes, thank you very much. So, sorry. I just want to make a little bit systematic regarding what I understand. So, Dr. Majid, he first showed the status of the storage with solid metal hydride and show some result or some progress or the roadmap of the Department of Energy, United States, which is very important to know. And I think such report, there are many reports on regarding Department of Energy in the United States. They are working very actively on this topic, and I invite the student to go to internet and to provide or to get the or report or always last report about hydrogen from different institutions in the United States, and to read it in detail if you want to understand what Dr. With the speaker have say. Then he talked about his own results, which is called resultant discussion. And there I would like to say some comment on it. The first question is addressed to Dr. Majid. How much atom are you studying exactly to show these results? About something like 160 or something like this? Dr. Majid, do you hear me?
Yes.
So how much molecule do you use in your calculation?
In the metal organic framework, in the 424.
424. Okay, this is very important because you know that the density, the quantum mechanics and the density function theory, it's done for a small amount of atoms.
Yeah.
And it's limited by the number of atoms if you want to have the convergence, etc. And I think Professor Benyoussef is there to correct me. The questions now, we are not going to stay on just showing what is possible on small amount of molecule. What is your strategy if you want to extend to a large amount of atom and to go to large scale? How do you want to do this? Do you understand my question?
Majid, have you answered to the question of Professor Ennaoui?
Yeah. Do you hear me, sir?
Yeah, you have the floor.
Please, can you hear me? Can repeat your question, Mr. Ennaoui?
So can you show up, because we don't see you anymore? Your video camera.
Yeah.
Okay, now we can discuss. So my first question was how much molecule? You says me 400 and something like 400. Then I wonder how to go to the real problem, because we want to go from knowledge development to research and development. And research and development mean you will prepare some material in the lab, and then you will make some measurement. And when you prepare material in the lab, it's something like gram or milligram and so on. So how this will be done? Because when your colleague, he talked about the project is going further on to even prototype. So I just want to make a how to situate the problem and who is doing what, etc. So therefore, I would like to have just an idea about how you manage. You are doing so. You make density function theory. That is fine. Then you have some results.
Yeah.
And how do you translate this in the lab?
Thank you for your question. The big challenge in the metal organic framework, this is high porosity, but always to study the density function theory, to avoid this computation covenant, we consider the new strategy or this work to simplify the system, this connector, or the other strategy, the equation, the passivation. But in the experimental or the reality is, I don't know.
Maybe you have for the DFT calculation, there is the symmetry is used and the periodic condition are used to simulate the infinite system, the thermodynamic system with finite one. And this is in statistical physics, it is well-known finite size analysis. We start from finite system and increase the size of the system and analyze the behavior of the property of the system by increasing the size. And then we can extrapolate to high size. And then we obtain what is called finite size analysis scaling. And we can have the behavior of the thermodynamic limit by doing calculation only on finite size system. This is well known in statistical physics and used also by Monte Carlo simulation for finite temperature, because density functional theory is for fundamental state, and this is as T equals 0 Kelvin. But we have to use molecular dynamic and also kinetic Monte Carlo to study system at finite temperature. And in this case, we use statistical mechanics to simulate a thermodynamic system using finite size system.
Okay, so this means that you have this possibility to have an approach between what is done in terms of calculation and what will be done in the lab. Okay, very good.
And already even for this the calculation done by Majid, 400 is a very high number for DFT, very high number.
It's too much.
It needs, too much.
I understand. Another question to Dr. Majid is why do you use this metal organic network 5, MOF5? Is because it's the most promising? And why you decorate with lithium? Why you use lithium decorated MOF5? Is that the system which is actually will go to the industrialization, or what is the reason for that?
Yeah, the lithium, the best element to link with the molecular hydrogen by the electrostatic interaction. And also the lithium is the lightweight, the mass to increase the gravity capacity.
Okay. I have the last sentences, and then I will give you the floor. Sometimes you use the reaction coordinate and sometimes the diffusion coordinate. What is the difference and what you can learn from both? You have in the horizontal axis for your experiment or your calculation, even the reaction coordinate and sometimes diffusion coordinate. Can you explain to us what is the difference?
Diffusion is to migrate this element between the set absorption, and the coordination reaction is it's a formation energy. It's a reaction between the product and react.
And how do you know this when you are making your calculation? Do you choose this in the theoretical background, or how do you choose this?
yeah, for the diffusion or the migration in H2, there is the need to determine the different pathway between in the surface materials. But for the metaorganate, it's parameters to stability, the structure.
Okay, okay. Professor Benyoussef,
Yeah.
I don't know if the other guy is still here, the one who presented the project. I would like, you can maybe address him one question because it's very important.
Je suis toujours là, monsieur.
Okay, very good. So I don't see you, but I see your photo before, so it's fine for me. I want to know, your project is a huge project. It starts from fundamental part and then to go until the prototype and so on. You want to even have electrolyzer and of course, if you have electrolyzer, this means you want to produce hydrogen, and if you produce hydrogen, you want to store it, and all this go to a prototype. So the time for the project, is it enough to do all this stuff?
Si vous permettez, je peux répondre en français.
Of course, of course.
Oui, vous avez raison. Quand on voit la quantité, bien sûr, des sujets qui sont abordés au niveau de ce projet, on peut dire que les 3 ans ne seront pas suffisants. Mais on a déjà commencé avant, bien sûr, l'attribution de l'accord de financement. Donc, on a déjà commencé l'étude de ces différentes domaines. Par exemple, si on prend la partie de stockage solide sur les matériaux, il y a plusieurs étudiants qui ont mené ces études, et parmi ces étudiants, il y a Majid Kassaoui. Donc, on a déjà une idée générale ou même une idée détaillée sur le process d'absorption, process d'absorption, etc. Ce que je peux vous dire, c'est que les lacunes dont on a actuellement et sur lesquelles on travaille, c'est la partie de la configuration du réservoir. Donc, l'enceinte porteuse qui pourra bien sûr porter ces parties et qui nous permettra bien sûr de restituer cet hydrogène qui est absorbé ou même de mener l'absorption si le réservoir est déchargé. Donc, c'est ça la partie sur laquelle on travaille, surtout avec nos partenaires français qui ont déjà de l'expertise là-dessus. C'est puisqu'on a comme partenaire la société Jomi. La société Jomi, actuellement, les directeurs de cette société, ce sont eux qui ont réalisé le premier prototype du réservoir à hydrure de magnésium, qui était présenté même au niveau de la présentation de M. Majid sous le nom de McPhy. Donc là, actuellement, McPhy ne produit pas, bien sûr, ce type de réservoir, vu leur coût qui est élevé à cause de la matière première. Donc, du coup, cette entreprise a pris tous les locaux de McPhy réservés à cette installation, et ils ont bien sûr l'expertise, ils ont déjà un prototype, et on estime également développer avec eux notre propre démonstrateur. Donc, on ne va pas seulement prendre ou acheter ce réservoir, mais on va essayer également de mener des études, co-études entre leur bureau d'études et nos étudiants pour essayer de développer certaines parties. Ça, c'est côté réservoir. Pour le côté électrolyse ainsi que la pile à combustible, nous, personnellement, à Rabat, on ne va pas détailler, surtout pour la pile à combustible, mais sauf pour le couplage de toutes ces technologies. Mais pour les détails de fonctionnement des matériaux internes, de la caractéristique ou la configuration interne, par exemple, de la pile à combustible, on ne va pas s'en charger puisqu'il y a déjà une étude des étudiants qui mènent cela à l'ENSA, surtout côté électronique. Donc, c'est pour ces raisons qu'on ne va pas se focaliser sur la partie interne de la pile à combustible, sauf la partie de production. Comment étudier son comportement avec que ce soit lié directement avec l'électrolyseur ou directement avec le réservoir. Donc, nous, on va analyser et simuler le comportement avant, bien sûr, l'installation. Pour la partie électrolyseur, sur papier, il n'y a pas indiqué qu'on doit mener une étude sur les matériaux électrolytes, mais on a simplement évoqué comme quoi la production d'hydrogène sera une production d'hydrogène vert et pas via la vaporéformage. Donc, on va utiliser des électrolyseurs. Mais en parallèle, il y a déjà une doctorante qui est Omaima Ben Abdelillah qui a présenté la semaine dernière, qui va se focaliser sur le côté interne de cet électrolyseur. Donc, pourquoi ces 3 années, on pourra dire que ça suffira, ça sera suffisant, puisque nous, de notre côté, noir sur blanc concernant le projet, on doit avoir une idée vers la fin sur la conception générale du réservoir, sur la mise en place de toute la chaîne. Donc, mais pour les parties auxiliaires, que ce soit l'étude d'électrolyse ou l'étude interne de la pile à combustible, donc ça sera en parallèle. Ça pourrait bien sûr être fini avec bien sûr la fin de la thèse de chacune de ces étudiants qui mènent ce travail.
Okay,
donc, j'espère que j'ai bien répondu à votre question.
Oui, bon, moi, je voudrais seulement que ce projet soit clair pour ceux qui s'y intéressent, surtout, disons, si un jour une industrie au Maroc regarde ce vidéo, ils savent exactement.
Je comprends.
C'est pour ça que j'ai posé ces questions-là. Donc, chacun va faire son effort pour délivrer.
Tout à fait, la partie qui est réservée.
C'est la partie qui lui est confiée, et puis à la fin, tout le monde,
voilà,
chacun doit s'occuper de son délivrable. Ok, très bien.
Voilà, raison
donc,
pour
moi, j'ai
terminé.
Thank you very much, Professor Ahmed Ennaoui et Dr. Mohammed Haji. Now there is question for Majid Kassaoui from Nasir Boukraoui. He asked how we can know the good materials of our purpose by the interpretation of the data when you get it from DFT method. Majid?
Yeah.
Can you answer?
Of course. There is several advantage or the criteria to good materials in hydrogen storage. For example, the stability, the kinetic, the gravimetric capacity, or the volumetric capacity. For the second question, probably to avoid the expensive trial and the error processes for the experimental laboratory.
Have you read his questions in the chat?
Because he asked what's the maximum molecule we can calculate with the server or the cluster in your laboratory.
Yeah.
Maybe the 400 you said before is the number of atoms you have done.
Not cluster, but the number atoms. Yeah.
Okay, now I open the floor for question from the audience. Are there some question for Majid or for Haji Mohammed? I have a question, Majid.
Yeah.
Storage depend on the disruption temperature.
Yeah.
And for MOF, metal organic framework, and for 2D materials, the challenge is to higher the disruption temperature. It's very low. Are there other applications for storage at low temperature. Other application than domestic one. In mobility for cars and so on, we need temperature around room temperature. But maybe for other application, we can store hydrogen at very low temperature. In this case, maybe these materials are useful for that. Have you some idea about other application?
Maybe this other application, but not the higher desorption temperature, but the lower desorption temperature. For example, the absorption or the gas absorption.
Yeah.
But the higher, I don't know.
Okay. Are there other questions? This lecture series will continue weekly every Friday at 6:30 p.m. The next lecture is will have is scheduled for Friday 24 at 6 p.m. It will be given by Dr. Fatim Zahra Mizat. She will talk about material perovskite, oxide perovskite for hydrogen production using photocatalysis. I invite each of you to submit an abstract to present your research work. This is an opportunity to discuss your research result with the scientific audience. It's a good opportunity. You have to take it. Are there some other questions? Okay. If not, we can close this session, and we will meet next week, Friday at 6:30 p.m. And thank you for your attention. See you next week, and bye.